The problem of optimal path planning is a highly researched area in academia which has found its way into implementation in many industrial areas. Google Maps is a widely used product which rely heavily on the implementation of path planning algorithms, image processing, satellite navigation and sensors board system. Autonomous vehicle would be the another implementation of path planning algorithms. This system would hit the road in next 5 years in all developed countries. And another field of implementation is automated manufacturing, where we need to get the fastest material removal or addition time under given constraints. Roads development in rural areas in unexplored areas is also done by the path planning problems. In this project, we have developed a GUI framework which allows us to analyze theories on the basis of performance, areas of explored region, limitations, and on dynamic environments, as we will see in the upcoming slides. We have analyzed three algorithms: dijkstra's, A star, and D star or dynamic A star. A GUI is developed for validating the implementation. A grid map of 60 cross 60 cells is used for 2D visualization of the problem. We are giving the coordinates of goal and target as input along with the map, and we can set the shape and the position of obstacles arbitrarily. In this, we are doing a simulation which allows us to visualize the explored regions by all the algorithms and see what is the final path. Final lengths of the path are calculated for validating the optimality. We are analyzing on the basis of complexity, time complexity, distance traveled on the basis of number of cells and the actual path of the shortest path, and we are at the end going to analyze dynamic environments where our map is changing continuously and the grid map given at one point of time would not be validated at another point of time. At the end of presentation, we are providing the future work. For the implementation, we have choose C++ due to its higher executing speed, better memory management over MATLAB. We have used simple and fast multimedia library SFML for designing a graphical user interface. A map is converted into a 2D array of cells containing information of their current state. The information of current state is stored as binary, 0 for obstacles and 1 for clear path. Though this implementation can be extended to a continuous valued representation, like if we want to go on a mountain or a water region, we can use any value between 0 and 1. The cell also contains the information of its parent cell and whether it has been explored or not. In the next slide, we are going to see the GUI, which is implemented by SFML. The SFML library basically contains 5 modules, which are Windows, Graphics, Systems, Audio, and Network. We will initially be analyzing two algorithms, dijkstra's and A star. The color coding is done like unexplored cells are white, blocked cells or obstacles and walls are black, start and end cells are blue and red respectively. The yellow area is the explored region, and the shortest path by dijkstra and A star are in green and pink respectively. For drawing a GUI, we have designed a 800 cross 600 pixel dimension. The implementation consists of 3 main components. First is main loop, which is also known as game loop, which runs 60 frames per second. Basically, these are images running at 60 frames per second, which will be showing as an animation in the upcoming slides. Another component is dijkstra's program and another is A star program. All three components are simultaneously run by multi-threading. Obstacles can be drawn by dragging mouse over the map. When the user clicks any button, the program runs in parallel. The yellow cells are all the explode cells which a program explode during its time. When the path reach the goal, the program stops working. Dijkstra's algorithm is a greedy algorithm for the minimum path. For the implementation, we have allowed movement across all 8 directions. The horizontal and vertical movement cost is set to equal to 1, while the movement along diagonal is set to equal to root 2. The algorithm starts by filling each node into an open list. There are two lists, open list and explode list. Explode list contain the vertices which have already been explored, while open list contain the nodes which are currently being processing. Initially, explode list is set empty. Now we have a distance array also. The distance of source vertex is set initially to 0, which is the distance of any node from the source, and the distance of source from itself is set equal to 0. During the loop, we trying to find a vertex with the minimum distance. If that vertex happen to be goal, we break the loop. Otherwise, that minimum vertex is removed from open list and put into explode list. All the cells which are in explode list are yellow color coded by the main loop. And there is one condition for updating the neighbors of the find minimum node. If that any neighbor is suboptimally calculated in previous iteration, then it would be updated here. It would not be updated if that cell is blocked. Like this black cell is blocked, so it would not be processed or updated. It would not again be updated if it is already in the explode list. Like any yellow cells would not be processed in the further iterations. And last, we are returning the parent list, which is basically the path found by the dijkstra's. Here we can show the implementation. Right now we are filling the obstacles. These are certain obstacles. When we click the dijkstra's, it starts working, and the yellow cells are all put into the explode list, and the green cell or the green path showed the final minimum path. It covers a distance of 55 cells. In order to show that dijkstra's algorithm find the global optimum, it has two properties: optimal substructure and the greedy choice. It says that the final solution consists of intermediate steps, while the intermediate steps are themselves the optimal path from the source, the greedy choice. It says the final solution is achieved by selecting best or optimum solution at each iteration. Like here, at each iteration we are trying to find a vertex having the minimum distance at that particular vertex. At that particular time, it may not be lead to the global optimum, but at the end or the termination of the algorithm, we are guaranteed to have a global optimum. Like we can show here with an example. Here we have three choices. The program makes the choice with a minimum value, so we would go here. Now this cell will update its neighbor. The neighbor of this cell happened to be the goal. So the goal value would be set to 27. Now the program again runs and it finds the cell with the minimum value. The thing is to be noted here is that we do not terminate the program while finding the goal. We would only terminate the program when the goal would be put into the explode list, and the goal would be put into the explode list only when it happens to be the cell with the minimum distance value. Right now it is not the cell with the minimum distance value, so the cell which is happened to be the minimum distance value is here. It is 5. So 5 would be explored and it would be put into the explode list. Its neighbor which happened to be a goal again would be updated. Here we have a value of 25 which happened to be lesser than its previous value 27 from the previous iteration, so goal would be updated to 25. And again the program runs and it finds the cell with the minimum value which happened to be the 11 here. Goal is currently 25, so the program takes the cell 11, try to update its neighbor which is goal, which would not be updated in this case because the sum would be 11 plus 17, 28, which is greater than its previous iterated value 25, so it would not get updated. At last goal would be the remaining cell so when this line seek the cell with the minimum distance, then goal would taken out and it would be put into explode list and the program terminates. A star searches almost as fast as a pure greedy heuristic space algorithm like best first search, while it also maintains the optimality of Dijkstra's algorithm. In the implementation, we have allowed movement across all 8 directions. Like the previous implementation, we have given the horizontal and vertical cost equal to 1 while diagonal cost is set equal to root 2. The search direction which is provided only in A star, which is not in Dijkstra's, is guided by the heuristics function h. It tells us how much minimum distance the current node still need to travel to the goal. Like the heuristics function of this node would be the straight line. Heuristic function is taken out to be the minimum distance in an unobstacle environment. Each cell in this implementation contains the information of how much distance it has traveled from the source, which is called cost so far, equal to g. H is the distance it still needs to be traveled from current cell to the goal, called heuristics function calculated by heuristics function known as h, and the total cost, which is the sum of g plus h. The implementation of A star is similar to Dijkstra's with some minor changes. Like here we are doing open list and explored list while we were doing earlier, and we are updating all the values of GHF to be infinity for all the vertices except the source node, which is set to be zeroed. All the vertices are filled into an open list, and the parent of each cell is initially are undefined, while at later stage of exploration they are defined to be the cells from which they are coming, which can be seen in this main loop. The main difference from the Dijkstra's occur to be here we are taking the vertex with the minimum distance dot f, which is the total cost, while in Dijkstra's we are taking the vertex with the minimum cost so far or the distance dot g. That's the main difference. While everything remains same, like the minimum cell is going into the explode list updates its neighbor. Here for updating neighbor we are calculating g H and F values while updating its parent to be the cell which we removed on the basis of distance.m, and when this open list got empty, or when we got the goal, or when we don't get the goal, then the path is returned to the main, which color coded the final path in pink color like shown here. We have the implementation video here. The final path consists of explored cells of this much yellowed cells only, while in the case of dijkstras we have filled all over the region while calculating the minimum path. While the minimum path happened to be the same in dijkstras and A star, like we can see that in dijkstras we covered all the region while getting up to the minimum path. Okay, so here we see that, okay, so it's another implementation. When we run A star, it is only going into the direction of the goal, not covering all the region because of its heuristics function, which only guided it towards the goal, and the cost is 55, which is same as that of dijkstra's optimal path. Now we are going to discuss optimality versus speed criteria. When we overestimated the path calculated by the heuristics 400 times of the actual path, then A star gave 6 extra cells to reach the goal compared to dijkstra's program. Though the time was much lesser than A star and much lesser than dijkstra's, so the calculation of the heuristics depend on our implementation, what we required at that condition, optimality in distance or optimality in time or quickness in terms of speed. For the calculation of heuristics, we have given horizontal and vertical cost equal to 1, diagonal cost equal to root 2, and dx is the difference of the abscissa while dy is the difference of the ordinates, and heuristics is a function of dx dy and the cost which we have allotted, so it must be chosen wisely according to our condition. Here we have an example to prove our case and to analyze some results. First we would run A star by multiplying its heuristics function by a value of 400 times. So when we run here A star, it would be the A star of which heuristics is multiplied by a factor of 400, so it would be very much faster. Like here we can see that it just explored the region of interest and nothing else, and when we run dijkstra's we can see what will be the optimum cost. The cost calculated by overestimated heuristics is 61 while that of dijkstra is 55. Now we are going to see the actual A star. It would give the optimum path in the minimum time, though its time is greater than the greedy algorithm which was the first implementation, but it gives the 55 steps same as the dijkstra's. When heuristics is highly overestimated, then both A star and dijkstra took almost equal time during a highly underestimated heuristics, while during overestimation of A star it is much faster than dijkstra's while also deviating much from the shortest path. We have implemented open list as STL set container. That overall time complexity of both dijkstra's and A star happens to be the big O V log V, because the main loop consists of OV iterations. If all the cells would be iterated and the goal would happen to be the last cell, like here we can see that almost every cell has been explored. So we can see that dijkstra's and A star both are giving the same time complexity, but A star is much faster because it eliminates or put nodes into explode lists on the basis of total cost F, which is also a function of heuristics, and heuristics is a greedy function which always directed towards goal, avoiding any regions like this and this. Here we have a video to show that, like, first we when run a star, it would not go here and here, which are the unnecessary regions, only going towards the goal, like here, which is obtained in 100 steps, while when we run the dijkstra's algorithm, it searches almost equally, and it also gives 100, but it is in a much larger time. So that's the difference the total cost F causes. The next step would be to plan for dynamic environments. The dynamic condition implies to continuously changing is the cell's state. So in order to detect whether we have an obstacle or not, we are continuously scanning an area of radius 5 cells unit around the vehicle. Following two methods are used to avoid obstacles in changing environments: recalculation and splicing. Recalculation: when an obstacle is detected in the proximity of vehicle, then vehicle stops at the current cell and recalculates the whole area from that current cell to the goal. While in splicing, instead of going from the current cell to the goal, we reutilized the previous calculated path, so we save the extra calculation. It is done by connecting the current position to the immediate next position after the obstacle in the original calculated path, and this way we merge alternate path, like from this to the original path when this obstacle appears in the path. Here we have an example. Here first we initially calculate the shortest distance from source to goal, while when say our vehicle reaches up to this cell, an obstacle appears, so we do recalculation. Though splicing is a better algorithm, but we use recalculation. So here when reaching here, when it detects the obstacle in place of its path, it stops at that point and recalculates the shortest path from this position towards goal, which is shown in green here. The future work in this project would include extracting clear paths and block regions from a top view image in form of a grid map. The image can be obtained from a high quality satellite pictures or overhead drone transmitting continuous image of the environment. Next, in order to decrease the converging time, we are going to implement convex hull around the concave obstacles to get the faster converging times. And we would like in the real life grid states are continuously changing, so we are going to implement D star and LPA star and D star light, which are basically the three algorithms discovered in the last decades for the dynamic environments. Lastly, we are going to implement RRT and PRM, which are probabilistic algorithms, which are still much faster than the A star, but they would not allow us to have an optimal path